Let us check where we ended. Please keep your microphones in muted mode, right? Is my whiteboard visible?
Yes, sir.
Yes, sir.
Yes, sir.
Yes or no?
Yes, sir.
Okay,
Yes,
thank you
sir.
so much. Okay, okay.
Yes, sir.
Yes, sir.
Okay, so this was what we ended the last day's discussion, right? Okay. So are you finding this subject interesting? Because the more you interact with me, the more energy I am supposed to get, right? Okay,
Yes.
so we ended, we ended with notational conventions to check on the recursiveness of the patterns of strings that are being generated via finite automata, right? Yes. And for that, I took the example of del hat, and I would just have a very short recollection, and then I enter this algebra, right? Okay. So what I was talking about is, see, there are two ways to perceive a finite automation, right? One is the machine approach, designing a machine, and another is algebra, right? So one is notational, and another approach is design of machines, right? And what we have seen is um, for uh, for for DFAs, we introduced working with strings. Now we are interested to work with strings to find out how automation accepts strings, right? We want to perceive how a finite automata behaves when we deal with strings. That is our main objective, and based on that concept, we will be talking about um, an algebra that would follow certain rules of derivations, so that we can derive strings in an algebraic way, right? And always we are going to find the equivalent counterpart with the machine part, right? So in case of DFA, we told that we extend the function del. What was del? A very short recollection. What was del? Del was a mapping function that was mapping your ordered pairs of Q cross sigma to Q, right? In case of a DFA, right? We extended del so that now it works on strings to del hat, something called del hat, and we defined del hat Q comma W to go to a state P, because it's a DFA. If we start at a state Q, you are always going to end in another state, a single state, deterministically. So if it is QW, it is P for sure. Now, what was that W? By notation, W is a string now. So by the basic definition of del, it was del Q comma a symbol that was taking you to P. Now we extend this symbol so that it works with W. And by the recursive nature of this derivation, I will show you how it looks. It is said that you can define something called del hat if and only if with del hat you go to some, you break W to look like A followed by X. X is another string and A is a symbol, right? So you say, or rather you say that it is XA. It is a string. W can be thought of as W equal to a substring X followed by a symbol. So string followed by a symbol makes W. Okay. So del hat Q comma X comma A. So if and only if del hat Q comma X takes you to some state R such that del of that state R and A is P. That is what I mean to say. So it states that you can work with strings if and only if there are physical intermediate states in between. So if states doesn't exist, this definition is going to fail. It is true if and only if on del hat, if you go from Q to X, if that state is R and if that state exists, A del of R comma A is P. So we rewrite W as X followed by A, and we say that del hat of QW is P if and only if there is a state R such that del hat of Qx is equal to R and del of RA is P. Got my point? Yes or no? So it states that physical states must exist. So if I think of W as a string like this, A, B, A, B, A, so intermediate states at every intermediate position should exist physically. So if I start at del Q comma A, I should be going to say R, then del of R comma B, this B, I should be taken to some R1, then del of R1 comma A, I should be taken to somewhere called R2, then del of R2 comma this A should be P. If this is true, then only del hat of Q, you started at Q and you went through physical states by parsing one symbol at a time. And all these four symbols make up a string W. And if this is true, only then you say that del hat of QW is P. Now the question is how to verify that such states, such intermediate states really exist. How to verify? How can we verify that these intermediate states really exist? So what can be done is we should be constructing a method that would fail if no such intermediate states exist. Right? Did you get my point? So we should be constructing a method that would fail if no such intermediate state exists. And by that method we'll say that if it fails, that means there was a gap in constructing the finite automata. There was a gap in defining the states and their properties so that you can go from A to B, then B to A, then A to A. Right? And what is that approach? That approach is a recursive approach. So what you say? You say del hat of QW is equal to del hat of QX comma A. Right? Then again break X into something like X1 B and go on deriving like this. Del of dot 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 dot. Finally, you find del hat of Q comma A, where A is the leftmost symbol of the string, right? And then you go on with other symbols, S1, S2, for example, symbols, right? If it gets complicated, let me write B, A is like that, B, C. And it says that the derivation starts at the core point where you have a definition available for what is del hat Q comma A. And for DFAs, del hat Q comma A is nothing but del of Q comma A. Do we agree? So in case of a DFA, In case of a DFA, del hat of q comma a, that means transition on a string, because a single symbol is also a string. Del hat of q comma a is del of q comma a, and you surely need to have a state for that. You substitute that state at the innermost point, right? And then you have del p comma b, something like this, p comma a. And if del p comma a exists, then only you go on reducing the whole equation. So intermediate states must exist. Otherwise, if it doesn't exist, it fails somewhere in between, and the recursion is never complete, and the derivation is never complete. So incomplete derivation is an indication that you had faulty design. Now, this very recursive nature gives you the advantage to check at each step whether such intermediate states exist. That is what I mean. So I wanted to give you the flavor of recursion that may not be available from the machine construction part, right? Because viewing the machine, you cannot have a whole sense of how the strings are parsed and constructed. So in case of NFA, the same thing happens. In case of NFA, del hat of q comma w will be defined in the same way. Del hat of q comma x, and del of that, thinking of w to be x followed by a. The only difference with the DFA and NFA is now this is nothing but a set of states capital P, that may be a set of states P1, P2, right? Pk, a finite set of states, right? That is what we denoted with del hat of this is ultimately a set of states. And at the core of the recursion, what you find? Del of, you go like this, and you ultimately find del hat of either q comma a, the leftmost symbol, either q comma a, the leftmost symbol. So del of, you go like this, you get either q comma a, or you can also find you'll find del hat of q comma a. And in case of NFA, again this is a set of states, say q1, q2, q3. Now in case of NFA, what you do, there is a del after this, right? So let us concentrate to this portion. So what turns out is del of q1, q2, q3, comma b. Let us concentrate on this part. What is this? This is a union of I equal to 1 to 3 del of pi b. So for each, del of qi b. So for each q's, you have to calculate what is del of q1b, what is del of q2b, what is del of q3b. You have to take a union. Yeah.
Sir, after Q1, Q2, Q3, nothing is visible, sir.
Nothing is visible?
No, sir.
I
thought you
Why?
It is not the whiteboard is not updated.
Yes, sir.
After Q1, Q2, Q3, del of.
After
Del
q1,
of-
q2, q3.
So now it's
Del
updated.
of-
Sir.
Now it is updated?
Yes, sir.
Okay. So shall I be talking a bit slow so that it gets
Sir,
synchronized
actually,
with my hand?
a bit slow, sir, because I think there's a latency issue within the time you're writing.
Okay.
Isn't it, sir?
Okay, so it is not matching. Okay, let me talk a bit slow so that I synchronize with hand speed, right?
Yes, sir.
Now, is it updated? Is it updated?
Yes, sir. Yes.
Yeah. So in case of NFA, this is same. But in case of epsilon NFA, what would be the case in case of epsilon NFA? In case of epsilon NFA, del hat of q, you start at q, and you are parsing your w, and you are checking what are the strings what are the states that I'm going through to accept W, and I accept only if I reach a final state, right? And this is true for epsilon NFAs, NFAs, and DFAs. So del hat Q comma W in case of an epsilon NFA, you should not write directly something like this. Rather, I would take epsilon closure of whatever I do, right? I will take an epsilon closure of, now I will do del of del hat Q comma X comma A, right? Yes or no? Is it
Yes,
updated?
yes, yes, sir.
Yes. So to be safe, I will take an epsilon closure. So how does the recursion look like when expanded? The recursion looks something like, if the length of W is say 5, you will have 5 dels, right? So del, 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 it would go something like this. And at the innermost part, you have del Q comma epsilon. So Q comma epsilon was absent in case of NFA, because in case of NFA, del hat of Q comma epsilon, remember epsilon is a string, so I need to have a hat, right? So in case of a normal NFA, del hat of Q comma epsilon was Q only, because you were not allowing transitions on epsilon in case of a simple NFA. In case of a simple DFA, also you did not allow transition on epsilon. So del hat of Q comma epsilon for simple DFA was P, if P was a state, right? Sorry, Q. So if Q is the state, on an epsilon you are not allowed to change state and you remain in Q. In case of normal NFA, also you were not allowed to change on epsilon, and you started at Q, you remain at Q. So del at Q epsilon is Q. I write in curly braces because this is NFA, and I don't write in curly braces, rather write simply because this is a DFA. But in case of an epsilon NFA, the innermost core part of the recursion stands out something like this, right? Right? Yes, agreed? Now, what is this? You need to define this. Now, you again recursively define epsilon, del hat of Q epsilon as epsilon closure of Q. Do you remember? So this portion, del hat of Q comma epsilon for case of epsilon NFS is defined as epsilon closure of Q. Now that may be some states P1, P2, P3, right? That Q may go to P1, P2, P3, a set of states, because it's an NFA. It will go to a set of states. So it may go to 3 states P1, P2, P3 on epsilon. So to be safe, this del hat is interpreted as epsilon closure of Q, and you have some P1, P2, P3, something like this, right? Now what you want to do is you have to calculate del of P1, P2, P3, comma A. And as usual, it would be, what is this del of P1, P2, P3, comma A? As usual, it will be an union of I equal to 1 to 3 Pi del of Pia. And you go on calculating like this, you go on recursing like this, and expand. But before you exit, don't forget to have an epsilon closure of everything. So it is epsilon closure of everything, right? That is, so this whole thing looks like this. Is it clear? Now I gave you a feel of this recursiveness of how strings.
So 1 second, sir.
Are
Sir, that recursive part is also an
realized.
epsilon closure, sir.
Yes.
So that
Once
recursive
more.
part. So that recursive part is also it is also an epsilon closure of the recursive.
Yeah.
Okay,
You,
sir.
you didn't get my point, right? So let me illustrate again. Let us take some time. Don't worry. So in case of epsilon NFA, you want to have an idea of, you are starting at Q, how you consume W, right? So there is a machine equivalent for that. You start at Q. You are getting, say W is ABA. So on A, you are going to P1 and P2. This is an NFA, right? Is my whiteboard updated?
Yes, sir. Yes, sir.
Okay, and then on B you go somewhere. This is how you design an epsilon NFA, right? And maybe there are possible paths on epsilon also. So that's why if for epsilon NFA del hat q comma w, in spite of the fact that w may be a b a, there may be epsilon here. That means a followed by epsilon, a followed by two epsilons, followed by b, followed by a single epsilon, followed by a, followed by epsilon, followed by a. So your string may be actually this, but in essence you write a b a, right? But since you allow transitions on epsilon, there if you think of all possibilities, you can think at the uh, at the most aggressive way of thinking is you think of empty spaces being filled with epsilons. And what if your epsilon NFA has transitions on those epsilons? So if you start at q, okay, on q you can get epsilon and go to p, and at p actually you get an a, right? So
Yes.
that's why, to be safe, yeah, that's why. So what is del hat for normal NFA? It is del of del of del of, it goes on like this. And finally del hat of q comma a, and then b, then c, it goes on like this, right? But in case of an epsilon NFA, you need to be absolutely sure that you don't miss epsilon paths, right? So epsilon closure of everything. And also in the innermost part, so you think of del hat of qw. So del hat of qw, you think of this as epsilon closure of, one minute, my whiteboard is syncing, epsilon closure of that particular recursion, right? And at the innermost part, it is del hat of q comma a b c. Now to generalize, it also may be epsilon closure of, and actually it should be del hat q comma epsilon, right? A b c, something like this. Why? In order to take care of the front epsilon, if it exists at all. What should you do? If it exists at all, what should you do? Because the innermost part is the leftmost symbol of the string. So in order to take care of this, now what is del hat q epsilon in case of epsilon NFA? In case of epsilon NFA, del hat of q comma epsilon is epsilon closure
Of Q.
of q, right?
Yes, sir.
So you take care of that epsilon. Now your recursion is safe. And also in this case, the recursion will fail at any point if intermediate states are not defined. That is what I mean. So the very basic definition of del hat has that recursive seed inbuilt, so that you can have a recursive view of the strings that are being parsed and realized with your machine. That is what I mean. Now based on that concept, that so you have an intuition now, right? Intuition. You have developed an intuition based on all such studies that you made right now. Right now we discuss something. Now what is that intuition? That intuition is that the regular sets are recursive. Now I'm not going to a full proof for this, but you have an intuition, right? If I am going for a full proof, I would have been calling it a formal theorem, but I'm calling it as intuition. Now we'll use that intuition to define an algebraic notation for regular languages. What do I mean? An algebraic notation capable of expressing a regular language, right? And what is that? What is that algebraic notation called? It's called a regular expression. It's an algebraic expression that expresses the language. So before we go into the detail of that, how does it express? Let us come back to that example. The example that we took: any number of A's followed by any number of B's followed by any number of C's, and epsilon NFA. We talked about this, right? Now, what is the language of this? From that intuition that you had developed, that from that intuition, the language is any number of A's followed by any number of B's followed by any number of C's. Now, what are these any's? Let us decode what are these any's. Any number means either 0, it means any means 0 or more. 0 or more, right? 0 or more, any. So in this picture, the interpretation, the machine part of the interpretation was, on an epsilon I go here, I start here at Q0, on an epsilon I go to Q1, on an epsilon I go to Q2. So I don't have a string at all, I have an empty string, right? Another interpretation is, I start here, I don't take any A's, I slip to Q1, take a B, any number of B's, 4 B's for example. Again on epsilon, I go to Q2 and take 5 C's and accept. So 4 B's and 5 C's are accepted. So 0 A's. There are no A's. So either 0 A's or any number of A's followed by either 0 B's or any number of B's followed by either 0 C's or any number of C's, and that as an expression. So this was an English like expression of the language, right? And the language that is accepted by this epsilon NFA can be written as epsilon, a single A, a single B, a single C, a double A followed by B, A followed by C, B, in some order, right? All possible strings. So a set of all possible strings that are being taken care of by this machine is called the language of this machine. Now, since this machine is a epsilon NFA, and we have theorems that says epsilon NFA is equivalent to NFA is equivalent to a DFA, it means that this is a regular language by name, right? So how can we have an algebraic expression? How can we have an algebraic expression that express the same set of strings? And that expression is, from an intuitive point of view, is A star, B star, C star, star denoting that AD. Got my point? Any number of A's followed by any number of B's followed by any number of C's is an expression. This is an algebraic expression that is capable of expressing this whole set of strings. So if you ever have this expression, it means you have a whole set of strings, something like this. Is it clear? For example, if I have 0 star, what does that mean? It means a set, 0 number of zeros, that means epsilon, or you can have a single 0, you can have 2 zeros, you can have 3 zeros, you can have 4 zeros, like that. Infinite set. What is this called? This star operation is a spatial operation called clean closure. Is my board visible?
Yes, sir.
Okay.
Yes, sir.
Now, what is this operation called? It's called a clean closure. Now, how to formally define clean closure? It's very simple. Actually, this operation is associated with representing a set, right? So that means a language L. So we define clean closure over a language L. We define over this set. Does it make sense? So we define clean closure as if there is a language L, the clean closure of that language is union of Li. Now what is this Li? Number of times L is realized. Number of times L is realized. Right? So if L, if you talk about our alphabet sigma that contains symbols, what would be sigma star? Sigma star is realizing sigma 0 or more number of times. So I'm not realizing sigma at all, 0 realization. Right? Or you may have, you realize sigma once, you realize sigma twice, and have a union of all these things. Now, if sigma is your alphabet, is your binary alphabet 0, 1, realization of sigma once means either you take a 0 out of sigma or you take a 1 out of sigma. Right? So this very alphabet has an algebraic expression too, and that is called 0 plus 1. Either you have a 0 or a 1. Right? This plus means or. So realization of sigma once means either you take a 0 or a 1 out of this alphabet. Realization of sigma 0 times means you don't take care of sigma at all. That is epsilon. Right? And you realize sigma 1 once means either you have a 0 or 1. You realize sigma twice. What does it mean? In the first realization, you may have a 0. In the second realization, you may have a 1. So you may have a string 0, 1. Or in the first realization, you may have a 1. And in the second realization, you may take a 1 out of this. You take a single symbol out of these two symbols with probability 50, right? Or with probability half. So this is another valid string of sigma square. So what is sigma followed by sigma? It is sigma square. So another realization may be first time you take a 0 out of this set, and for the second realization you take another 0. So 0, 0 is also a valid string. Another realization may be you take a 1 in the first realization, and in the second realization you take a 0. So all these are strings of sigma 2, right? So how do you write this? How do you formally write this in terms of closure operations? So what you say is that if L is a set, if L is a set of strings from sigma star, right? What is sigma star, by the way? A set of all strings possible by combining all symbols of sigma. So sigma is their alphabet. It is finite. It has finite number of symbols. So just like 2 sigma elaborates all these 4 strings, similarly, star sigma means all possible combinations of all possible strings made out of all possible symbols of a finite alphabet sigma. So if L is such a set, if L is such a set, then you define the clean store operation as a union of realizations of L. It may start with 0 realization, it may start with 0 realization, and it may go up to infinity. So this is what is clean closure operation, right? And regular expressions, the expression that is capable of denoting a whole regular set is basically recursively designed with some basic building blocks. Now, what are the basic building blocks? Just think of the base cases of your recursive definitions. So it says that once we are, since our main intention is to express a whole set, we say that, okay, we will deal with the empty set, right? And we say that phi is a regular expression that denotes empty set phi. Another building block is epsilon is a regular expression that denotes the set epsilon. You say that for all single symbols, so for all single symbols A, which is an element of your alphabet, A is a regular expression. A is a regular expression. I make it bold somewhere so as to distinguish with the symbol A. A is a regular expression denoting the set A, right? And finally, you say that if considering 1, 2, and 3, if R and S are regular expressions, so are R plus S are concatenated by S and R star. So these are the 4 basic recursive steps to define a regular expression, which is an algebraic expression that is capable of expressing sets. So by the very basic definition, you define the basic building blocks. Either it is phi, or it is epsilon, or it's a single symbol. You define based on these basic building blocks, and you say that what this symbol, if it is a regular expression, what this symbol denotes. It denotes the empty set phi. So it denotes some set, right? It's phi. Epsilon, if it is a regular expression, it should be capable of denoting the set that contains epsilon. A, if it is a regular expression, it should be denoting the set A. So by these building blocks, if you define regular expressions R and S, now that's the recursive part, right? If you have regular expressions R and S at your hands, then R plus S is also a regular expression. R dot S is also a regular expression. R star is also a regular expression. What is plus? The union, set union operator. So here plus is or operator, right? What is dot? It's string concatenation. Yeah, string concatenation operation, right?
Yes,
And
sir.
what is star? Yeah, it is clean closure operation. Okay. So with these basic building blocks, if you define R and S to be regular expressions, so R can be phi, S can be epsilon, right? R can be a single symbol, S can be another single symbol. Whatever it is, you substitute whatever it is, R plus S. If R and S are regular expressions, then R plus S is also a regular expression. R dot S is also a regular expression. R star is also a regular expression. Right?
Yes, sir.
Yes? Okay.
Yes.
So this is how this says that there are several proofs, and I like to go through proofs, but I'm afraid that if I now start going through proofs, I'll be wasting much time. So if anybody is interested, actually this corresponds to an algebra that I was talking in the last portion of the last class, and that is called clean algebra. Clean algebra, right? So if I impose clean algebra to define regular sets or regular expressions, regular expression is nothing but a clean algebra that operates on operators like plus, dot, and star with epsilon and phi as the basic building blocks. So this is an algebra, right? And since it's an algebra, it has axioms formal axioms, that 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 are always satisfied. Now, if anybody is interested, or if we can arrange for some extra class, I will show how this clean algebra, actually this regular expression, see this is a way of construction, right? This is a way of construction. So recursion is a way of construction. So we constructed regular expressions recursively. Recursion is a way of construction, and with that concept of del hat, we have seen that recursion is a very proper formal way of construction, so that you can have a check at every point whether certain things formally exist, certain structure exists, and if it exists, only then the recursion is allowed to move forward, right? It is allowed to terminate. Otherwise, it will just terminate in an unacceptable condition. So recursion is a way of construction. So you construct the regular expressions with recursively like this. But actually, the regular expression is an algebraic structure that follows certain axioms. And those axioms are nothing but, it says that, okay, if plus is interpreted as union, that is as or, then there should be certain things like certain, and if phi is one such key building block of this algebra, so it should be that if P is a regular expression, P or phi is P. This is, for example, rule number 1, right? If P is a regular expression, P plus P is P. This is very obvious because P or P is P. Got my point? If P and Q are regular expressions, P plus Q commutes. Because if plus is interpreted as union, it doesn't matter. P union P means P or Q. It is same as Q or P. Right? Similarly, with the dot operator, you can have operations. With the dot operator and epsilon, you can have operations like, say, epsilon followed by P. If P is a regular expression, epsilon followed by P is always P. If P is a regular expression, P followed by epsilon is always P. Right? If P is a regular expression, P followed by Q followed by R, I am giving brackets just to categorize. Just to categorize. This bracket has no meaning, right? So it will be same as P, Q, R. Again, these are rules. These are rules that define the concatenation operation, right? See, here it was commutative, but concatenation cannot be commutative. So PQ means you concatenate Q after P ends. It can never be equal to QP. It's not possible, right? Is it possible? If P is a regular expression denoting some string in the minimal case and a set of strings in the maximal case, and if Q is a regular expression, then P followed by Q can never be equal to Q followed by P. So this dot operator doesn't commute. The plus commutes. What is the star operator? The star operator has certain definitions, and those definitions you can think of something like, if P is a regular expression and if Q is a regular expression, the closure of P plus Q should be P star Q star, right? Something like this. And if you say that, okay, P is a regular expression, then it's called sum star operation, and you have other certain operations. If P is a regular expression, Q is a regular expression, PQ star is 1 plus P QP star Q. So this is how star is defined, right? Again, you have a star star operation. If P is a regular expression, P star star is P star. So that is what I mean by if you find time, you just go through clean algebra. If you don't find books or papers, I can supply it to you,
So what is P star
and
star?
you will see. Yeah, this P star star, if P is a regular expression, the clean closure of P is P star, and then again you take a clean closure, right?
Okay, sir.
So P is a regular expression, you take a closure, clean closure of P, that is P star. You again take a closure of P star, right? Whatever amount of closure you want to take, it always turns out to be P star, right? So this is how star is defined. So each of these operators, plus, dot, and star, are defined. This union or concatenation and clean closure are defined as an algebra. Algebra means if the algebra is complete, it means everywhere substitution is possible. You can substitute any of these axioms with any with any values, right? And it says that it is a complete algebra. The regular expression is a complete algebra over plus, dot, star, and with epsilon and phi as base elements. So here phi, why did I write phi? So yeah, here. So phi here is a base element in case of addition, in case of ORing, in case of ORing, and in case of concatenation, epsilon is that operator, right? So you can define, and it turns out that algebraically this thing, how to realize, how to build regular expressions. For building regular expressions, you define, you go for recursive construction like this. Step number 1, phi is a regular expression that denotes the set phi. Epsilon is a regular expression that denotes the set epsilon. As for all symbols A, some dark A is a regular expression that denotes a set A, right? If R and S are regular expressions, so are R plus S, R dot S, and R star. So algebra is a theoretical way of defining properties of strings that this regular expression algebra should decide, and how those axioms should look like. What are the things that needs to be satisfied? How things can be derived from that. That is the objective of the algebra. Now, if you want to realize the algebra in some practical way, you need to construct the structure in a practical way. Then the best way is to define it recursively, for the reasons that I was discussing in case of when I was showing the Del hat operation. That is why I started with the Del hat operation, right? And in the machine equivalent part, so what do we see? That phi is a regular expression that denotes the set phi. Epsilon is a regular expression that denotes the set epsilon. Every symbol that is an element of an alphabet is a regular expression that denotes the set A. Built upon this, if R and S are regular expressions, then R plus S, R dot S, and R stars are regular expressions. Now, what do they denote? If these are regular expressions, what do they denote? If R is a regular expression and if S is a regular expression, they should be denoting some sets, capital R and capital S. So R plus S is a regular expression that should be denoting R union S. R dot S is a regular expression that should be denoting strings X followed by Y, such that X belongs from set R and Y belongs from set S. Is the interpretation correct? If R is a regular expression, R star is a regular expression. What do I mean by this? It means if R is a regular expression denoting the set R, then R star is a regular expression denoting the set R star. Done? Did you get the essence of this way of expressing things? Algebraic way of expressing a set of strings, right? Now, if you go through an example, for example, okay, so the algebra also says, if you go to the algebraic part, the algebra also says that out of these three operations, there is a precedence associated with the operations, and the precedence is this clean closure is the highest precedence. It is higher than the concatenation, and it is higher than the union. Union comes at the last. In somewhere in the middle is the concatenation operation, and star is of highest precedence, right? So if we talk about a regular expression, for example, 0, 1, star 0, 0, 1 star plus 0, it is actually, it should be thought of as 1 star. You should associate 1 star very tightly with a 0 because it is concatenation, and then with this. So you can put brackets to have the real field. So this should be evaluated first. When you are talking of validating strings or examining strings, this should be evaluated first. Then this should be evaluated, and then this. And when you are talking about construction, this should be constructed first. Then this portion should be constructed. Then this portion should be constructed. Okay? Is it? Yes or no?
Yes, sir.
Okay, so I think you have a class, so I'll be leaving
Yeah, sir,
you.
we have a class,
And
sir. Our voice system.
yeah. I'm sorry. So please go through clean algebra once, so that we can have a more detailed discussion. Right? Done?
Yes,
Yes
sir.
or no? No replies?
Yes, sir.
Okay.
It's okay. Thank
Yeah.
you.
So,
Sir,
okay.
another thing, can we get this thing, I mean, this board, and there is a
Yeah,
share option, I guess. So,
there's a
the
share
link,
option.
yeah, in blue.
Okay. Now there is a,
Well,
1 minute. Let me check if I share. Okay, board title. 1 minute.
Sir, I guess that will just share the.
Invite link. Yeah, enter emails to invite from Gmail.
So that will just
Um,
enable us to edit that whiteboard, sir. That won't share
okay.
every content.
Sir, just switch off the
Okay.
candidate part, sir. Like the you don't give us access to edit, sir. So in that
yes,
case,
sir,
So
then
that
it
would be
will
fine.
make some problem. Just change
Okay.
the candidate
So
permission.
what exactly do you want? Do you want to write on the board along with me?
No, sir, we just want
What do you
to
want?
see the board.
Okay. Are you following when I am writing the board?
yes, sir.
So you can, I
Yes,
guess
sir.
you
Oh,
can
that is
download
that
it.
is that is most important, because my board work is not good, right? Because I scribble on the board too often, so if you go back and look at the board, hardly it will carry any formal meaning, right? But anyways, this somebody should be recording these videos, and you can listen to the video once. That can be done.
Yeah,
So
okay,
you
sir.
can
Thank you.
save it, sir.
And
This whole screen.